Good afternoon, everyone. Welcome to our pre-lab lecture. Our experiment today is on colligative properties, in particular, determination of molar mass of compound. You should have two reagents in the Ziploc. Please refer to Ziploc with the label experiment number 3, colligative properties, determination of the molar mass of a compound. The handout for this experiment, the procedure for this experiment is available online. It is posted in module number 3. Um, Let me share my screen here, show you where the module for experiment number 3 is, colligative properties. If you click on the home page for the course, there is the modules. You need to click and scroll down to module number 3. That is determination of molar mass of a compound. It's our experiment today, determination of molar mass using freezing point depression. We will have a quiz at the end of the session. You don't have to be on the Zoom conference while taking the quiz. However, I'll be available just in case you run into technical issues, or if some questions are defective, I should be able to come and assist you where applicable. So remember, I know I mentioned we will take the quiz, but I'll just go over the overview of the experiment, what you need to do, how to collect the data. Then from there, we take the quiz and we call it a day. Remember, pre-lab assignment for this experiment is due tonight, and the data sheet is due next week. Let me share my whiteboard here. I believe you are taking the course right now, and you should be, or maybe you are almost starting the chapter on colligative properties. Colligative properties. All right. Colligative properties are properties of solution which depends on the number of particles dissolved in a solution, not the nature, but the number of dissolved particles in solution. And there are 4 colligative properties you should learn, not for this course, but just to be well-rounded. For your own benefit, if you're taking the course right now, you need to master all the colligative properties. One is favor pressure lowering. That means the vapor pressure of pure solvent is always higher than the vapor pressure of the solution. You lower the vapor pressure of the solution. There is an equation for that. You may be asking an exam, calculate the vapor pressure of solution. Please refer to the class text. And then there is the boiling what? Boiling point elevation. That means raising. To elevate something is to raise. What this means is the boiling point of pure solvent is always lower than the boiling point of solution, or rather the boiling point of solution is always higher than the pure solvent. Change in boiling point and the subscript P here, you saw this in the background, is given by I, which we call Van Hoff factor, times subscript P, we call this molar boiling point of a given solvent. And the italic M here stand for molality. So this is the equation for determining the change in boiling point between what? Between the boiling point of the pure solvent. So if we are to determine the temperature, it's going to be boiling point of solution, SLN, minus boiling point of charged solvent. All right, solvent. You can use this equation or you can be given. The M here, you should know M is molality, and this is determined by finding the number of moles of solute, which means you should know what a solute is, what a solvent is, over mass in kg of not solution but for solvent, mass of solvent in kilogram. At this point, you are expected to be able to use dimensional analysis, know the correct conversion factor. You need to convert the mass, all right? The mass of the solvent from grams to what? To kilogram, from mass to kilogram. Of course, everybody knows this equivalent statement. 1 kg equals to 1,000 grams. You may not be given, but you are expected to know. There are some obvious equivalent statement you will need. So that is an italic M, which stands for molality. If you are not given the number of moles, all right, if you are not given the number of moles, you need to find an again of solute. And by the way, solute solvent, solute is present in small amount, solvent present in large amount. That's the difference between the two. If you are not given the number of moles of this solute, not solvent, I meant to say solute here, what is being dissolved, you will always have to use the periodic table, which is basically mass in grams of molar mass. This means if you are not given the number of moles, you're only given what? The mass of the solute and the chemical formula. The chemical formula, you'll have to use the periodic table to find the molar mass. Sometimes you may be given. So going back to this equation, the molality, the italic M stand for the number of, molality, and you may be given or you may be required to calculate by first finding the number of moles divided by the mass in kg. Now I here, I understood this is called Van Hoff factor. Van Hoff factor. And this stands for the number of dissolved particles, or basically, this is number of dissolved particles. It will recall, you will be required to recall the concept of ionic compounds and molecular compounds. It will call for classifying the solute as either electrolytes or non-electrolytes. Electrolytes, they ionize, they dissociate in H2O or in solvent to give out particles. For example, sodium chloride, NaCl, you should be able to see where the cation is, where the anion is. I for this is two particles. If something such as calcium hydroxide, this is the formula for calcium hydroxide. I for this is 3. Where is it? We have 2 hydroxide ions and 1 calcium ion. So you should be able to see where the compound will break apart, will ionize, will dissociate to help you you can have a compound such as this. Just give you how you look at the or determine I. Magnesium phosphate, PO4 with a 2 there. This means we have three magnesium ions, 2 positive, and 2 phosphate ion, PO4, 3 negative, and the total I for this is 5. I for this is 5. So you should know that how many particles will have, and this is for electrolytes. These are for strong electrolytes. It's basically ionic compounds where you have either metal and a non-metal, either metal and a polyatomic ion. Let me just label this as for electrolytes. Here, electrolytes. That means they dissociate. On that. And then for non-electrolytes here, B, non-electrolytes. Non-electrolytes are those compounds which do not generate ions in H2, such as sucrose, okay? They do not dissociate in H2O. They do not generate ions when dissolved. For all electrolytes, I is always 1. I is always 1. So you have to know which compound is an electrolyte or non-electrolyte. I can give you an example of a solute, which is I see common in this section. Glucose, for example, glucose is sugar. When you dissolve sugar, it will not conduct electricity because it does not ionize. E.g. here, sucrose, all right, ethylene glycol. That means the antifreeze in your car radiator. When they dissolve ethylene glycol in H2, it does not dissociate. Problems here, you may be, given information that for a non-electrolyte, or this is a non-electrolyte, it was dissolved in that. And then once you know it is non-electrolyte, okay? Once you know it is non-electrolyte, then you know I is 1, so that when you plug in this equation here, you will have to use 1. Molar boiling point constant will be given for a particular solvent. You will be given the I. This is just like the density equation that if you know I or one of these, 1, 2, 3, and then 4 here, you can, if you are given 3, you can calculate the fourth one. And then the third colligative property here is this is third colligative property, which we are going to use in this experiment is a freezing point, depression, freezing point depression, okay? Just like boiling point, change in freezing point, which means the difference between the freezing point of the pure solvent and the solution, delta T F subscript F for freezing point. What this means is the freezing point of pure solvent is always higher than the freezing point of this solution. This, in the same way, we use molar freezing point of the solvent, Van Hoff factor I is the same, and this is also the molality. Change in freezing point, all right, this is freezing point of pure solvent. Let's say solvent here, that's pure solvent, minus freezing point of solution, because solution is always lower than pure solvent, to get the change in freezing point. So for today's experiment, listen, for today's experiment, you should be able to identify the solvent, identify the what? Identify the solution when you mix the two. Critical is, what is my solvent? What is my, the solute, so that when you determine the freezing point for both, you will be able to plug in to get the left side of the what? Of this equation. To get the left side of this equation, you'll have to perform the experiment in such a way that you will have to use this equation to get the change in freezing. This means change in, this is change in freezing point between solvent and what? Solution. Between solvent and solution. Between solvent and solution. So if you know the left side of the equation, we will need to rearrange the equation to find the molar mass. From this equation, we have to rearrange or make the M the subject of the formula, which means this is going to be the molality equals to I times molar freezing point over change in what? Change in freezing point. The denominator in this equation, where I'm taking you, is how do we move from molality to the molar mass of a compound? To help you out, the I in this experiment, I will always be 1. Kp or Kf, that is molar freezing point, you have to see a handout. It is given in the handout. Change in what? Change in freezing point. This is experimental. That means you have to perform the experiment to change or to find the change in freezing point by plugging in your values from the experiment into this equation. You'll plug in into that equation. So you can do that. You can get the molality, but the left side, let me call this equation 1. Let me call this equation 1. That is equation 1. Then there is another equation 2 here. Number of moles is given by mass in grams of solute of molar mass. So you need to understand or find out what is the chemical formula for your solute. And then from the direction, from the procedure, this is from the experiment, what the direction called for. How much do you need to weigh out of your solvent? I think there are 2 trials. One is 0.4, the other one is 0.3, we'll see later. Then this one, you can use the periodic table. So once you know the number of moles, all right, number of moles from this equation 2, you can now therefore molar mass is given by this is a standalone equation. The number of moles from here, we can find the molality. Remember, molality is given by number of moles, sorry about that, we will use this number of moles of solute of mass in kg of solvent. So this is equation 2 you will need this equation 2. From the first one, right here, you can rearrange to get the molality this over that. This is equation 1 from the experimental data. Now, this equation here is what we need to rearrange to get the number of moles. Number of moles, therefore, of solute is given by the molality times kg of solvent. This is equation 3, which you will have to have. There is equation 1, there is equation 2, and then there is equation 3. So if I can determine from the experiment the molality, I mean the number of moles of solute, I know the molality. Where are you going to get the molality from the experiment? From equation 1 here. You see this equation 1? It will give you the numerical value for molality, which you will have to plug it here. The mass in kilogram of the solvent, of course, the direction will state how many uh, grams of solvent you need to weigh out. Change that to kilogram, you'll get the number of what? Number of moles. And of course, now molar mass, do not Google out. Molar mass from the experimental values is given by mass in grams, whatever you will weigh out of a number of moles, of the solute. Recall, the units for molar mass is grams per mole. So this is from the experiment, This is what you will need to remember on how you will find the molar mass. Real quick, let me just go through the handout here. You will see how to, for part 1, you'll determine the freezing point of the pure solvent. You'll determine the freezing point of the pure solvent. You should have the paper towels, either microwave. This is just for boiling the water, all right? And either stopwatch, timer, doesn't really matter. For part 1, you'll determine the freezing point of the pure solvent. How will you know that the pure solvent, this is the freezing point of the pure solvent? The direction called for boiling water to around 80. It is essential that, all right, it is essential that all the crystals, or, the solvent or any solute you place in the test tube should dissolve. Please make sure that once you place in the test tube, it should completely dissolve, all right? You'll record the temperature as when it gets to 65, make sure you dissolve everything inside the test tube. Should dissolve. Let the temperature drop from 80. Once it gets to 65, this is for pure lauric acid. Once it gets to 65, and please record to one place of decimal. It's important that you record to 3 significant, to one place of decimal. That's the temperature reading for every half a minute or 30 seconds. You can use minutes. How you will determine the freezing point for both solvent and solution is when the temperature is constant, like 4 readings. This is what I wanted to bring. How you will know that you have reached the freezing point. when you have collected at least 4 readings, all right, which is no longer changing. That is the freezing point of your freezing point of your pure solvent. You do the same thing for what? This is how you will, this is what I was looking for. Continue starting record temperature every 30 seconds until the temperature readings remain constant 4 times. That is the freezing point. It will flatten out, it will come down. Once you see that it is constant, and then that will be something like this. If you are to draw the graph, and the 4 consecutive will flatten out, just giving you that it will come down and it will start. You have 4 readings. You can take the average to get one numerical value for the freezing point of the pure solvent. You will repeat the same thing for the solution, but this time around, you'll have to try with the 4, you'll try with the 2 samples. So you'll just have to do the same experiment, but this time around, this is the mixture. 3 grams of and 0.4 and 0.5 grams of benzoic acid, 3 grams, 4 grams. Look at the data sheet for the solution. Here is the pure solvent, here is the solution. You are using 2 samples of benzoic acid. Trial 1, 0.4 grams of benzoic acid. Trial 2, 0.5 grams of benzoic acid. And remember, just like in part 1, for pure solvent, it's the lauric acid, you will collect the data until you see that 4 consecutive data collection remain constant, that it is starting to flatten out, and then that is considered as the freezing point. If it goes beyond the given 10 minutes, please just feel free to use extra. Just feel free to use extra scratch papers for data collection. You need a camera, by the way. When you see this one, it means you got to take a picture of your experimental setup. When you get to step 13, something similar to this means, or not similar, but this means take a picture of the experimental setup at that point. This is just a stopwatch. Other than that, that is what I want you to do. You will submit this work next week. Next week by midnight next week, I'll collect the data sheet for this by or through. All right, through the Canvas. You have to submit your work through the Canvas. I see, Danielle, you have a question. When we take a picture of the crystallizer, do we include it in the main X? Yeah, you will attach it, not really, it will be like, when you save your data sheet on the desktop, when you click upload, you can also attach the picture, and then I'll see that you perform the experiment and you saw what I'll see on the picture. You will include in the submission. Yes, thank you. That is what I'm looking for. I hope that answers your question. Danielle, you'll have to include. Other than that, I'll just, you may lose points for not including the picture. Any other question? And by the way, I do have under the assignment, you'll have just to go into the respective folder. Please do not use any other folder to submit your work. Somebody previously, they didn't submit their work, and let's say, for example, we get to experiment number 8, and you are attaching experiment, or you are submitting experiment number 8 with experiment number 3, all right? That will count as 0, because when I get to experiment 8, I only expect to see the information relating experiment 8. I don't want to see anything in experiment number 8. Even if it is pre-lab for that experiment, you cannot submit the pre-lab along with the data sheet. Other than that, I'll stop sharing my screen and make the quiz available. If there is no other question, you'll have 40 minutes to take the quiz. I will be on Zoom conference. You don't have to be on Zoom conference to take the quiz. Any question before I make the quiz available? I'll assume that there is no question. And remember, you need a scratch paper, you need a calculator to take the quiz, you need a calculator, you need a periodic table. You may need a periodic table just to be, make sure that you don't start looking around. You have 40 minutes to take the quiz. You have 40 minutes to take the quiz unless you are eligible for extra time. I've taken account for that. I was notified, and those who are eligible, I notify them via the email. It has been accounted for. Other than that, thank you for tuning in this afternoon. I'll see you again next week, same time. Just hold on. I'm going to pause, because if I leave or end the session, that means I will be offline. I will pause the recording and make the quiz available. Thank you.